Hi everyone, these are the section 3.9 notes on related rates. Related rates are word problems that relate a concept to time. And the way we solve these is by using implicit differentiation. So I have 4 examples here for you. We're going to work them out. Let's start with problem 1. Problem 1 says, air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. So I'm going to attempt to draw a sphere. We want to draw a picture for all of these to the best of our ability. That's a good enough sphere, I think. Draw the little center. And it says determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So for each of these, I have kind of a 5-step format here that I think helps us solve. So the first thing you're supposed to figure out is what is given, what is known. Over here in this sentence, it says air is being pumped into a spherical balloon at a rate of. So at a rate of means they just gave you a derivative. And for related rates, we're going to get used to not writing it with the prime symbol like y and y prime. We're going to do it d something over d something. Okay, in this case, if it's 5 centimeters cubed, cubed means volume. Per minute is time. So what's known is dv over dt. So that's how we write our variables in related rates problems. Instead of, this really means v prime, that's what it means, the change in volume, the rate of change of volume, but we're going to write it with respect to time. Equals, it says 5 centimeters cubed per minute. Now, had it said air is being leaked out of a balloon, we would have to put a negative on the 5. Determine the rate at which the radius of the balloon is increasing. So what is unknown? Determine the rate at which the radius of the balloon is increasing. So what we want to figure out is dr over dt, the rate of change of radius, equals, that's our unknown. And with the unknown, there will always be a when. Always. So star this one. It is your job to write in the when statement here. It says, determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. So I'm going to write d equals 20 centimeters, d for diameter. Now, I have a problem here about volume and radius. So I'm thinking it would be best to rewrite our when instead of diameter equals 20 as radius equals 10. Because we know that a radius is half of a full diameter. Part 3 of every related rates problem is you have to think back, prior knowledge, to some formula that you know that relates the given variables. So it says, what equation or formula do you already know about the problem situation? Well, we're dealing with the volume of a sphere. So we have to remember the volume of a sphere formula. And we will do enough of these, and there's only a few that you have to remember. This is one of them. It says volume equals 4/3 pi r cubed. You're going to have to remember that. Memorize that one. All right. So since you were asked to find a rate, right, what is unknown? We want to find dr over dt. We want to find the rate of change of radius per unit of time. Since you're asked to find a rate, what process must you go through? Implicit differentiation. Okay, so we're going to take our v equals 4/3 pi r cubed formula. Left to right, we are going to find the derivative of this formula. All variables, I'm stressing to you, all variables are going to be treated implicitly. That means after every variable, there's going to be a times d something over dt. Instead of like a y prime, we're going to use this notation. So the derivative of 1v is 1 dv over dt, right? Isn't the derivative of v prime? Well, this is v prime, equals, I'm going to do the power rule here. 3 times 4/3 is 4. Pi is still, it's a constant. So 4/3 pi times 3, I'm doing the power rule, is 4 pi. R to the second power, because I'm minusing 1 to the degree, times dr over dt. Like I said, with related rates problems, because we now have 3 variables, v, r, and time, t is the third variable, we're going to treat every variable implicitly. It says solve for the unknown. Okay, so make a note. Plug in the when statement after you have implicitly derived, not before. People are always tempted to take this radius, like 10 centimeters, and plug it into the formula. No, you're not allowed to do that until after you do the derivative. So this is our derivative, and into all the variables, we plug in what we know. It says up here, dv over dt is equal to 5. So I'm going to put a 5 here, equals 4 pi. R is this. Now I get to plug in the 10 into r, times, remember, dr over dt is our unknown variable. This is what we're looking for. So it's okay to leave this as dr over dt. And then you solve. You know, this is 5 equals, that's 100 times 4 pi is 400 pi. And so our answer to dr over dt, which is the rate of change of the radius per unit of time, in this case it's minutes, is equal to 5 over 400 pi, which actually reduces down to 1 over 80 pi. And we write the units centimeters per minute. It's not centimeters cubed because this is about the radius. The radius is one-dimensional. If it said dv, it would have been centimeters cubed. Or as a decimal, and I actually punched this in before class, before the note, sorry, 0.00398 centimeters per minute is the answer. So this would be the exact, this would be the decimal version. Okay, let's do another one. Problem 2. Okay, so this problem is about a ladder. Let's read it and draw it first. It says a 15-foot ladder is resting against the wall. Okay, so if this is the ground and this is the wall, this is the ladder. I'm using L for ladder. The bottom is initially 10 feet away from the wall. Okay, so this is the bottom and it's initially 10 feet away. Okay? So the bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 foot per second. So you have to kind of get a visual. If this is the ground, originally this is the ladder. You know, if it's 10 feet originally away from the wall. Here's the wall. Then the ladder starts here, but then we're pushing it towards the wall. So it kind of like scoots in. And so it'll end up taller on the wall. And then it's being more scooted in. Like so. So what's changing is not the length of the ladder. I mean, the ladder is the ladder. You're not making it shorter or taller. What's changing is this, how many feet you are away from the bottom of the wall. So, you know, as you're going in towards the wall, this 10 is shrinking. And actually, if this is the height, I'll say Y for height, of the ladder on the wall, and as you push the ladder towards the wall, that height is going to increase, right? So I'm actually going to not put a 10 here. I'm going to call the bottom X. I'm going to call the height Y. All right, so let's just draw a nice one. X and Y. L is L, and actually L, we can give it a number because it's constant. This is actually going to be 15, right? You can put a number in your diagram if it's not going to change. Like I said, if we push the ladder towards the wall, the ladder is not going to get shorter or taller, shorter or longer. It's going to stay 15. But these two dimensions will change. All right, so what is known? So we know the bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of. So what is known is some rate. And as this is going closer to the wall, that's going to be dx over dt. They are giving us a rate. So it's d something over dt. In this case, it's talking about the bottom, so it's dx over dt. Now it's, very tempting to write 1/4 feet per second, but you have to think, what am I defining x as in my diagram? I'm defining x as a horizontal distance between wall and the bottom of the ladder. As the ladder is being pushed in, what's happening to that length? It's getting shorter. Therefore, you have to manually put in a negative into your rate. How fast is the top of the ladder moving up the wall? Okay, so we are asking about y. That's the unknown. How fast is the top of the ladder moving up? So they're asking us how fast this y length is changing. So question mark. Remember I said with the unknown there will always be a when. Let's see. It says, how fast is the top of the ladder moving up the wall? 12 seconds after we start pushing. So when 12 seconds have gone by. All right, now it says, what equation or formula do you know about the problem situation? Well, look at this picture. We have a right triangle. What famous formula do we know for right triangles? Of course, the Pythagorean theorem. And so I'm going to use the Pythagorean theorem for this picture, and it's going to say x squared plus y squared equals 15 squared. And I don't have to call this L for ladder because it's not going to change. If you have a constant piece in your diagram, you can put in the number right there into the formula. So that's x squared plus y squared equals 15 squared is 225. All right, since you're asked to find a rate, what process must you go through? Implicit differentiation is what you have to go through. So left to right, we're going to derive this. So what's the derivative of x squared? It's 2x times dx over dt. There will basically be a times dx over dt after every variable that you derive. Plus, what's the derivative of y squared? It is 2y times dy over dt equals the derivative of 225, which is a constant, so that's 0. Solve for the unknown. Remember, the unknown is dy over dt. This is our unknown, which means that we have to plug in everything else. All right, so I've got 2 times x times dx over dt. dx over dt we have, it's negative 1/4. Plus 2y, we don't have that, dy over dt equals 0. So I have to fill in the x and I have to fill in the y. So this is going to be x, this is going to be y. But what are they? So it's not like you get to plug in a 12 because 12 is a time value. X and y are distances. So let's think of what x would be 12 seconds after 12 seconds have gone by. So if we started with 10 feet, started 10 feet away from the wall, we are scooting in 1/4 foot per second, and 12 seconds go by. Think about that. 12 times 1/4 feet. 12 seconds times 1/4 per second. That's 3 feet we have scooted in. So is x equal to 3? No. X is actually not equal to 3 because that's how much we're scooting in, and we have defined x as the distance between the wall and the bottom of the ladder. So if we've scooted in 3 feet and we started 10 feet away, x is actually 7. So when it said when 12 seconds have gone by, that was code for x equals 7. And then, so we can put a 7 here. How about the y? Well, we have a right triangle. This is 15. We're calling this 7. What's the y? We have the Pythagorean theorem we can use to plug in. So 7 squared plus y squared equals 15 squared. And when you solve, you actually get y equals rad 176, which I'm not going to bother to break down because I'm going to just punch it into the calculator. So this is going to be rad 176. Anyway, so you do the math, 14 times negative 1/4, negative 14 over 4, plus 2 rad 176 times dy over dt. And when you solve algebraically for dy over dt, feel free to use your calculator on this. You get 0.132 feet per second, which is the answer to our problem. This is how fast that top of the ladder is scooting up the wall. All right, let's do a third problem. So it says two people are 50 feet apart. And so I have a diagram for you. I should have said two people are 50 horizontal feet apart. So person one, person two, and they are 50 feet apart, okay? It says one of them starts walking north. So one of them, let's say this guy stays, but this one starts walking north. Okay, so now he's here, whatever, he or she. It says one of them starts walking north such that the angle shown in the diagram, and there's no diagram, so I'm telling you to draw it in. So this is going to be the diagram. We're going to have a triangle, and this is the angle that's being referred to in the picture. Such that the angle shown in the diagram is, here it is, here's the keyword, keywords, changing at a constant rate of. Changing at a rate of, that is a derivative. That's a d something over dt. Now d what? It's not dv, we're not talking about volume, right? It says d, it's radians per minute. That's d theta over dt. Now, do we leave it as positive 0.01 or do we put a negative on it? Well, let's see. You got to think about your picture. If this person is walking north and then further north and then further north, what's happening to this angle? It's becoming larger. So larger means leave it positive. If this angle were shrinking, I'd put a negative on it. Okay, what is unknown? At what rate is the distance between the two people changing? Oh, distance between the two people. Well, let's think. If the two people look like this, the distance is 50. Then the person who's walking north is here. So the distance between them would be this line. Then the person continues to walk north. So the distance between this person and this person would be this line until I get here, and that's the distance between the two people. I believe that's called h for hypotenuse. So when it says at what rate is the distance between the two people changing, that's dh over dt is question mark. Remember, with the unknown, we always have a when. When the angle is 0.5 radians. So when theta is 0.5 radians. All right. What equation or formula do you already know about the problem situation? Well, I mean, it is a right triangle. So a lot of people want to say, oh, Pythagorean theorem, Pythagorean theorem. But for the Pythagorean theorem, I have to be relating three sides. This side, and this side. I don't have anything here. What I do have, yes, is a right triangle. But I have a side, I have a hypotenuse, and I have an angle in the middle. If you think about SOHCAHTOA, okay, you can figure out which function is being talked about here. So adjacent over hypotenuse, that's cosine. So the formula we can use that we know is cosine theta equals adjacent over hypotenuse, 50 over h. So then we go and it says, what equation formula do you know? So this is the one. It says, since you are asked to find a rate, what process must you go through? So implicit differentiation, again, you'll notice every single time. I'm going to go ahead and rewrite, because I know I'm going to be finding a derivative. I'd rather not leave this as a quotient, but write it as 50h to the negative 1 power. So I have cosine theta equals 50h to the negative 1 power. And I'm going to implicitly derive this one, left to right, implicitly. That means after I find the derivative of everything, I should have a d something over dt after it. The derivative of cosine theta is negative sine theta times the derivative of the argument, which is times d theta over dt. equals, use the power rule to do the derivative of this. Negative 1 times 50 is negative 50. H to the, I'm minusing 1 to the negative 2 power, times dH over dt. All right, so then I have to plug in what I know to solve for the unknown, which was dH over dt. This is our unknown. That means I have to plug something in for everything else. All right, so it says negative sine theta. Theta is 0.5 radians times d theta over dt we have way up here in the known fact. So times, here I'll do it like this, 0.01 radians equals negative 50 h to the negative 2 power. I don't have h. Where does it say h equals? So I actually have to find h. I need to find h in order to plug it in, and then I'll have a times dH over dt. This is our unknown. This is the one we're solving for, but I need an h. So what I do is I go back to my original formula, and I utilize it. I plug in 0.5 radians into the formula. I have cosine of 0.5 radians equals 50 over h. Use your calculator. Make sure you're in radian mode. Okay, this is radians. Punch in cosine 0.5, cross multiply, do your thing, and you will notice that h is 56.975 feet. And that's what needs to go into here. All right, and so you take out your calculator, you punch in negative sine 0.5, it has to be in radians, times 0.01 equals, then you punch in 56.975, you raise it to the negative 2 power, and you multiply by negative 50, and then you divide both sides by this expression, okay? And you get dH over dt is equal to 0.311 feet per minute. How do I know it's feet per minute? dH means the rate of change of height. H was our hypotenuse, and it was in feet, the distance between two people. All right, let's do one more problem. And I think I'm only going to do part A and leave part B for you to try on your own, and I will show you the answer in class. All right, so last problem, hang in there. We've got a tank of water in the shape of an inverted cone. That's basically an ice cream cone, like this, okay? This is an inverted cone, something that will hold water. It says a tank of water in the shape of an inverted cone is leaking water. Okay, think about that, leaking water at a constant rate of 2 cubic feet per hour. So I want to go to the what is known. That's what's known. How fast water is leaking. And if it's leaking at 2 feet cubed, then it's d what over dt? It's dv, volume over dt. And water is leaking out. That means water is becoming less in volume. So you have to put a negative on your rate. All right. The radius of the base of the tank. So this is like the base of the tank right here. It says the radius is 5 feet. And the height of the tank, of the container, is 14 feet. Okay. And there's water somewhere in there. There's water. Now I want you to imagine a cone filled with water. I think you can imagine that the top of the water would be circular, and that this would not be the radius of the cone, but it would be the radius of the top of the water, and that this would not be the height of the container, because we know that's 14, and that's not changing. The container doesn't change. The level of the water changes as water leaks out. We can call that h for height. All right, it says, here's the question. At what rate is the depth of water changing? The depth of water is our h. It's the height of the water. So the unknown is dH over dt, question mark. Remember, we need a when. with the unknown. So at what rate is the depth of water changing when the depth of the water is 6 feet? So depth of water we are defining as h. So when h equals 6. All right, here we go. It says, what equation or formula do you already know about the problem situation? We need to remember the volume of a cone formula. So the volume of a cone, I will tell you, and you are responsible for knowing, is 1/3 pi r squared h. And then it says, since you were asked to find a rate, what process must you go through? Implicit differentiation again. There it is. Okay, so we're going to do it. But there's an issue with this problem. Okay, pay really close attention here. What two variables do we have? We have dv over dt and dh over dt. That means in the formula that I have, I am allowed to only keep v and h. Any other variable in my formula is not welcome. I cannot have an r in the formula. It has to go before I can find the derivative implicitly. Before. You have to replace it with something. And so what happens is you go to your picture and you realize, oh, I have two similar triangles and I can set up a proportion. In fact, I can go r over h, right, is equal to 5 over 14. That's called similar triangles and setting up a ratio. And when you, a proportion, sorry. When you cross multiply, you get 14r equals 5h. You want to solve for r. You want to say r equals 5h over 14 because you want to replace the r. And so you'll have 1/3 pi. You'll have this new r, which is 5h over 14, quantity squared times h. You'll want to clean this up a little bit before you find the derivative. So let's see, we'll have 25 on the bottom, on the top, 5 squared, 25. We will have a pi. We will have an h squared times h, which is h cubed. And in the denominator, we'll have 3 times 14 squared. 14 squared times 3, you guys, is 588. So this is our volume formula. Okay, let me write that here. V equals 25 pi over 588. And I'm going to write h cubed here because remember, this is a constant. So people get confused. What am I supposed to do? How am I supposed to find the derivative of v and then h cubed? It's simple. It's just a power rule. So left to right, the derivative of v is dv over dt. You use the power rule to find the derivative of this. 3 times 25 pi over 588 is actually 75 pi over 588. H squared, because you're reducing the power by 1, times dh over dt. And it's ready to go. You plug in what you know. So dv over dt up here is -2. Let me write that. -2 equals. We've got 75 pi over 588 times h squared. H is 6. Times dh over dt, which is our unknown in the first place anyway, dh over dt. And so you pull out a calculator, you crunch the numbers, and you get dh over dt equals, I have the answer to this somewhere, negative 0.139 feet per hour. Okay, remember the when gets plugged in after you implicitly derive. Always, the when gets plugged in after the derivative at the very end. I'm going to leave part B to you. Try it out. We'll go over it in class. Thanks for listening. Bye.